resume. So for the last talk of today, we are happy to have Tim Sulimov from PDMI, and who will tell us about quantum mechanics scattering amplitudes through the lens of homotopy transfer.
Good evening, everyone. Let me start by thanking the organizers of this conference for this opportunity, as well as for their hospitality here at Steklov Mathematical Institute. Today, my talk will be devoted to infinity-type symmetries. I'll try to give an expose of this topic using an example so simple that I hope everyone will be able to follow it. It'll be my priority not to lose anyone, so that this would invite some meaningful discussion in the end. So the example is from one-dimensional quantum mechanics. Let's start with just the free problem. Psi lives in some Hilbert space, and the energy is fixed and it's positive. This is just minus the Laplace operator. So simple stuff, right? Now, consider the following chain complex, or rather co-chain complex, but I'm not going to distinguish between them. It's no real reason for that. So what we could do is just get a differential that looks like this, H0 minus E, and then add just zeros here. That would also be quite interesting, but just for convenience further down the line, I'd rather put an odd Grossman number that squares to 0 here, and thus all right, so once again, I put a Grossman number here, and I choose these ones to be the same. And thus, the functions here will be multiplied by this Grossman number C, no big deal. So when we have a chain complex, what do? We look at the cohomologies, right? How do they look like? Well, this H0 and H1, they're very simple. Look, here, it's just the kernel of this Q0. And that's obviously just the kernel of this H0 minus E, which is exactly all the solutions with this fixed energy E. I'll denote it by this fancy K. So this is just a kernel of H0 minus E. And here, it's actually the same thing, although just multiplied by C, because the kernel is everything, and we just have to factor by the image. So, and since H0 is self-adjoint, that is actually the same K, though multiplied by this C. All right, these spaces are interesting because, for example, in scattering problems, we exactly study maps from K to K. In this, if we're studying one-dimensional quantum mechanics, these are just two-dimensional spaces. So, all right. Now, here we obviously have a projection pi, an inclusion iota, and the same here. And we can add a differential here that would make this these pi's and iotas into chain maps, and that would be just the zero differential. And again, here it doesn't matter. All right. So, so if you take first iota and then pi, you would obviously get the identity. But if you compose them in the other order, you shouldn't. However, for this choice of the differential, we can define a homotopy such that this iota pi, and the identity are just homotopic to each other. So here, I just write Q naught anti-commutator with H, and this H is the Grossman derivative, and then I get this H naught minus E, or rather E for convenience, inverse. What do I mean by inverse? I mean not the causal green function. I didn't add any imaginary infinitesimals. I mean either the principal value integral or the sum over all states that are not the chosen one. All right, so you can easily check that this holds. It's 1 second calculation, and here's how it acts. And obviously we can add the same ones, the same H's here, it would not matter. Now, when we have all of this data, this is called two complexes that are homotopically equivalent to each other. And for such complexes, there's a very nice perturbation lemma that states that suppose that we want to perturb this differential by some Q1 so that this sum is still a differential. Then there are very simple formulas which take a perturbative form for primed versions of all the objects. And for what we should add here, which I would call Q1 induced, so that the resulting system is still a homotopy equivalence. And the formulas are quite simple. Let me just write them here. So let A be 1 minus this H Q naught to the power minus 1. Oh, Q1, sorry. And rather Q1H. And then Q1. So this is just as a series, is just a sum of Q1 times H Q1 to the power n from 0. All right, so using this A, everything can be written rather simply. This is just pi A iota. And there are similar formulas for pi's, iotas, and the homotopy primed, but I'm not going to write them out, not to waste your time, because we don't need them today. All right, what's the point? What's the point of all this mathematical stuff? Well, if you look closely at this relation, you will see that this looks awfully familiar, and this is basically the scattering matrix. Although, because we took this special green function and not the causal one, we don't get the usual T matrix. We get what's called a K matrix. So we get a C, well, C is left over, times this K matrix. It's related to the T matrix in a very simple way, something like, yeah, depending on your normalizations, of course, but something of this type. So it has all the properties that, well, it contains all the data that T does. All right, so this is somewhat unexpected. We made what is called a homotopy transfer, and we acquired the scattering amplitude. So this K, once again, acts from K to K. And this contains all the scattering data. But there's nothing special about it. It's just a way to restate the problem. We don't get anything from it, because the only interesting relation there could be is that this squares to 0, but because of our C, it's trivial. So, and as I'll mention in the end, this part was kind of known before. So let me propose a modification of this procedure that yields some new objects and new relations between them. Suppose we have a symmetry of this full Hamiltonian, just this simple type. Or if we're fancy and we want more generality, we can consider a whole algebra of symmetries that might not even be commutative. We can just take SI with Sj. This is some Fij, Sk, and maybe even it even closes on this H0 plus V, as it happens in supersymmetry. And why supersymmetry? By these commutators, I mean supercommutators that respect the degree. So maybe there's some even J, Ij, H0 plus V. All right, so we have a symmetry algebra. Well, let's then write basically the same setup. We'll have some first space, then some second space, then maybe some third space, but we'll be only concerned with these two. And again, first we have this Q0, the same as last time, H0 minus E, and here as well. So the cohomologies are the same. So it's K, and here, well, the grading here will introduce a couple of more Grossman numbers. So you can either grade them by just the degree of the Grossman numbers, or just by the number of them. So it'll be simpler for this exposition to just take here stuff that is linear in C and this CI. Here it's quadratic, so it's like maybe CI squared, something like this. And let's add some Q1 that is of this sort. So if we have just one symmetry, just take like some C tilde or C1, S1. And if we have a whole algebra of them, take CI, SI, and then also, what is it? Fij, K, Ci, Cj, d over Ck. Why in this form? Well, because all of these relations then would be equivalent to the condition of this new differential being a differential. This can be easily checked. All right, so this is a deformation, again, just like last time. But this time, here, we'll get something more interesting. Look, again, there's the same H, nothing changes. But here, this Q1 induced would now contain quite a few interesting terms. Now, let's see. Yeah, so this Q induced would contain the old K matrix, as we expect. And it will also contain the C over dC, C tilde. I write C tilde because I'm only looking at the case where there's only one symmetry. So I say plus C tilde S. More complex cases are possible, but just let's start with the simplest one. Then here, like this? Is it better?
Right, clear. Is it?
Is this better? All right. So here we have a new object called SR, then DC, C tilde, SL, and then also minus DC, C tilde squared, SLR. Oh, what I failed to mention is that we want this whole term to be odd. That means if we take an even symmetry, we take C tilde to be odd and vice versa. Now, we'll be interested in a case of a supersymmetry. That's why C tilde is even, and that's why I allow this term here. All right, so what are these? What are these? Well, they have the form very similar to K. They look like this. This is SPR. Now, this G is this. And also V, G, V, G, S, and so on. SL is the same thing, but the S appears on the, oh, and then there's an iota. Here it's S plus S, GV, and so on. And SLR has these symmetries on both sides. So it's pi, S, GS, plus S, GV, GS, and so on. Now, oftentimes this symmetry is actually a sum of a symmetry of the original problem, the free problem, and some addition. In this case, we have this S naught factors out. We have C tilde S naught here. And these contain just this S1 everywhere. All right. So, so what's the point? The point is now the relation that this new differential Q1 induced squares to 0 is non-trivial. It actually provides us with quite a few, actually, in this particular case, 4 quadratic relations. Let me just write one of them. So if you square it and look at all the terms and require for them to cancel, you'll get something of this type. So this is a new relation that connects some well-known K matrix with these new symmetries. All right, but like, is it useful? Can it be used at all? Maybe there are some obstructions to this. How much time do I have? Oh, great. Then let's see how one can see these relations in action. So let's specify our problem a little bit. Let us work in the Witten model. It's just supersymmetric quantum mechanics. Q is some Grossman theta dx plus w prime. Q bar is d theta minus dx w prime. And the Hamiltonian of this supersymmetric problem is the anticommutator. Again, well-known stuff. Yeah, if we expand it, just to be completely clear what this problem looks like, we'll get this. And here we'll have a number that is either +1 or -1, depending on whether it's acting on bosons or fermions. And our wave functions will be decomposed into bosonic and fermionic parts. Okay, so if we want to calculate something, we would rather take some concrete potential and then check it. So as it turns out, on a line, this is kind of difficult to do, and I'll explain why. So let's start with a problem on a circle of radius r. There we can define all of those expressions, but they'll be just simpler because they'll be just matrix elements instead of some integrals and some, yeah, so basically all the integrals will be replaced with sums. Now, obviously, there's no like direct meaning to scattering in a circle, at least not an obvious one. But we're interested in the r goes to infinity limit. So this restriction, it follows that the energies are, they have a discrete spectrum. Now this, wait, I'm sorry, I'm running a bit ahead of myself. So what is the potential that we want to take? Let W prime be of this type. This be 0, this is minus a, this is a, and this is lambda and minus lambda. So it's like a step. Then if you calculate this stuff, you'll get 2 delta functions, one at minus a, one at plus a, one is negative, one is positive, and you'll also get a constant shift as is common in supersymmetric quantum mechanics problems. So yeah, that shift will just shift the energy by this amount, which is lambda squared over 4. Yeah, and again, the remaining potential would be just plus delta function minus delta function at minus a and plus a proportional to lambda. Now, this is very easy to work with. All the matrix elements can be computed very easily. So that's in this setting, we check that our relation holds. And our calculations, obviously I'm not going to give like any details, it's simple stuff. But the important thing is that all these operators K, SL, and SR, they're matrix elements. They behave as something times plus something over R plus something else over R squared and so on. So it's a series in 1 over R that starts with the constant term. And when you want to go back to this line, when you want to go to R equals infinity, you're just left with these terms, and that's the matrix element you want. However, this S naught is actually proportionate to R. And as R goes to infinity, this becomes just the delta at 0. But this is expected, as S naught acts from on shell to on shell. So obviously it has a delta peak there. So what does it mean for our relation? That means, well, if we look at it and try to grab the terms with the same 1 over R dependence, we'll get R here. And if we take a constant term here, so it's like 1, we see that there's nothing to balance it with. That means in this order, this is just the whole equation without that part. So it seems like we didn't get anything new. All right, but in all other orders in R, so for a problem on the circle, the further terms, say when we balance this 1 over R term with R, here we obviously can take these terms proportional to just 1. And that means this, and we checked it diligently as you do, and it works. So no big surprise there. Okay, but what does it have to do with the, with greater physics, so to speak? What's the point of this all? Well, actually, that picture with all these complexes and quasi-isomorphisms pi and iota was not made up by us. It is a very general recipe to describe any field theory at all, especially gauge theories. Usually it looks like this. They work in homological convention. I used cohomological there just for simplicity. I think it's more convenient. But so there, the picture looks like this. they have some spaces, the spaces of fields. And they all have meaning. Now, this is usually the space of real dynamical fields. So that would be some phi in the phi cube model, or A in the quantum electrodynamics or Young-Mills theory. Now here live gauge fields. So say, I don't know, it's denoted by lambda. Here we have equations of motion. And here, well, these are usually called just Bianchi identities. I'm not going to focus on them. I just want to bring your attention that in our theory, obviously, we didn't have any gauge symmetry. So we had only these two spaces. And this is exactly what they were. There was the space of fields and the space of equations of motion, because we wanted that Q acting on psi to be equal to 0. So that's why when we consider these homologies here, when we look at this minus first homology, we take the, or rather this one, the 0th homology. We take those fields that are 0 on the equation of motions, but up to gauge transformations. So these are exactly the physical space of solutions, modulo anything unphysical. And the condition that this original Q0 squares to 0 means that the equations of motions are not affected by gauge transformations at all. So again, a very meaningful thing to desire. Now, what do people usually do with this setup? Again, there are some quasi-isomorphisms, pi and iota. They produce some homotopy. And here, actually, let me be a bit more general. And instead of cohomology, write some just reduced space. I will not ask for it to be the homology. It can be quite a few different things, as we will see. Now, here we get some Q0 induced. What is the meaning of all of this? First of all, how do we get this Q0? Well, originally, we start with our problem, be it, I don't know, maybe Young-Mills, right? And there we have, say, equations of motion, something like, and then some, and then some quadratic part in, I'm not going to bother with the coefficients right now, and then also a cubic part in A. Something of this sort. This is without any gauge fixing, and this is the equation of motion. And what can we see? We can see that they have a linear part, which is taken to be this Q0 on fields, that is. And they have a nonlinear part, which will be viewed as this deformation Q1. Now, with gauge transformations, it's similar. In the same spirit, we have, let's say, the transformation of A goes as the derivative of the gauge field, and then the bracket, something of this sort. Again, we see that there's a linear part to be included in Q0 acting on gauge fields now, and also a nonlinear part. Now, you might ask, well, but this is, how can we add anything nonlinear here? Well, actually, we work in the space of L-infinity algebras here, because we allow these operations to be they're now acting not on just some simple spaces, but on graded symmetric algebras built from the simple space of fields. And now here, as a deformation, we are allowed to include some higher brackets. So here, if we had just, say, something of this sort, here we can add brackets and higher brackets and whatever else we want. Yeah, and they're built looking at the equations of motion. That's one way to do it, at least. Yeah, so there's another way through Batarin-Vilkovsky theory. I'll just mention it briefly. There we get this Q as the entry bracket with the mass direction. And if we expand it in terms of fields and anti-fields, we get something of this sort. Here are some constants, say A, then B1, B2, so on, Bn. Then there are some fields. Some of them may be anti-fields as well, depending on the index. And there's also the derivative. Well, yeah, it's fine. And here, these constants, this is where we read our L-infinity algebra directly from. So we look at these coefficients, all for n equals to greater than 1. For n greater than 1, we get all these nonlinear brackets. For n equals 1, we get the linear part, obviously. Yeah. So what's the point of this construction? Well, this reduced space can be pretty much anything we would like it to be. Say, if we build pi's and iotas and homotopies such this x1 reduced disappears, then this new theory, which is due to this quasi-isomorphism, is thought to be very much like the original theory, and rightfully so. We'll get a gauge invariant theory in gauge invariant variables. This has been done for quite a few problems, some in Young-Mills, in a little bit of gravity in a special background, but I won't give any details right now. But we can also say exclude just some of the fields from this space and build appropriate quasi-isomorphisms. Then what we effectively have done is integrated them out without doing any actual integrals, right? Usually you would write something like, right, here some phi's that you don't want, say phi bar, I don't know, phi tildes of the action that depends on both those you want and those you don't want. But this way, we don't have to explicitly do any functional integrals. Another way, just as what we've seen here, is if we choose these spaces to be the homologies with respect to the operators built using equations of motion, we will get this picture. And this result, that the induced differential turns out to be a scattering matrix, is actually universal. You get it for other theories as well. This is actually, it has been like implicitly, these L-infinity algebras, they have been implicitly seen in works even by like Zinn-Justin in his time, but explicitly people have drawn attention to this like 20 years ago, about maybe 30, yeah. And these quasi-isomorphisms, they turn out to be what builds the Lemon-Simanzik-Zimmerman formula. Okay. Yeah, and in this case, where these spaces are just homologies or cohomologies, this is called, this chain complex is called a minimal model, not to be confused with the CFT one. They have nothing in common, unfortunately, or fortunately, I don't know. So, it is a way to get symmetry, scattering matrices. How does our example apply to all of this? Well, it's simple. We don't just add this Q1 that we are required by like equations of motion, but we can also add anything that's still any deformation that contains those new symmetries that we want to impose or that we know are present in the system. So these obviously do not have to be like operators, as in our case. These can be also higher operations, higher brackets. And this way, our new relations that we get here, this Q1 induced, using both of these parts, if we then square it and set it to 0, we'll get a plethora of new, what we call infinity type symmetries that are not just of simple type, something commutator with something is equal to 0, but more of this kind, but even in diagrammatic form. So I guess this is pretty much what I wanted to cover. Thank you for your attention.
Okay, let's thank the speaker. Question?
Thank you very much for your interesting talk. My question is about symmetry. We know it from 1920s, and that the great picture Pauli and Heisenberg talked the problem of singularity of, for example, electrons, and we can call it restricted Lorentz symmetry. And if you want to impose such a symmetry, which indicates the interaction between electron, the quantum wave as a quantum wave, and the electromagnetic field as a gauge field, and is there any way to get rid of singularity of electron? Because as you mentioned, you have a delta knot here, which will be diverged at 0. Right, and the electron, when you want to calculate R tend to be 0. For example, the Coulomb force will be diverged. So is there any way, based on your calculations, to solve this problem, fundamental problem of electron and quantum theory? Thank you.
Hard to say, actually. Well, I can't quite see how this R relates to that one. And also the word that I used, like imposed symmetries, I'm not sure we can actually do this in this model. We can try, but I should say symmetries that are present, and we just want to manifest them. If we know them in the original formulation, what would their manifestation in terms of amplitudes be? Concerning your question about the electron and radius, I'm not sure that it is really related to that delta of naught or.
Because when you consider a delta at the right-hand side of your equation, definitely you have, for example, 1 over r or r squared in your energy or potential of your fields. So if one, it's a navy, just like a naive or simple thinking I have, if one put, for example, instead of delta at the right-hand side, based on your symmetry, like a wave instead of delta, is there any possibility that solve the singularity of electron problem?
Well, clearly, if you put some, say, a ball of finite radius, that would resolve the singularity, but the physical meaning of such a ball is questionable, right? I'm not sure how imposing any symmetries, say like a rotational one or the one provided by, I don't know, in this, I don't know, hydrogen atom, you get this Laplace-Runge-Lens symmetry, those kind of symmetries, how it would help resolve the singularity of a point electron. So my answer is, I guess we have to think about it. Yeah.
Okay, thank you, thank you.
So I wanted to ask about that picture. So it's a field theory case. So I don't quite understand, because for me the S matrix involves something like quantum necessarily. And at which step, like by computing cohomologies of Q, you quantize the theory? Or
that's a good point. That's very good that you mentioned, because here, this picture, this works best for, well, it works for tree level. So there's no implicit quantization here. To go to quantum case, you need to solve like the quantum master equation and work from there. It's a bit more complicated, and this is work in progress. So this picture is somewhat developed for the quantum case, but we don't have a simple example like to demonstrate our approach there. So yeah, you're right. This is tree-level, no loops yet. And as you can see, like by composing n-ary brackets, you still get like one output, right? So it's basically some diagrams of this kind. So it's tree level.
So it's something like the on-shell action, right?
Probably. I'm not didn't quite get it, but yeah, I guess so.
Okay, maybe another question. So the important part of the S matrix computation is that you split well, let's say Hamiltonian into free part, and well, you go to the interaction picture, right?
Yeah.
Where do you do this here?
Oh, this is precisely what we call Q0 is the linear part of equations of motion. So again, we get them from the action, or we can reconstruct the action from the equations of motion. It doesn't really matter. What matters is we either get the quadratic part of the action or the linear part of equations of motion. And this is what we call Q0. And and based on this Q0, we build the homotopy, these quasi-isomorphisms. So this all works in this non-interacting theory, and with the linear gauge transformations. And after that, yes, we add everything else. Here in this Q1, here it appears. And then we use this homotopy transfer to calculate the S matrix. So yeah, that's where we do it.
Thank you.
We're a bit late. Maybe the rest of the questions can be asked in private. So let us thank the speaker again.